Hello everybody. Today we'll be walking you through our final state design presentation for Sukup manufacturing and their cold rolling operations. So a quick overview. We'll start with an introduction and then pass through objectives and assumptions, review some alternatives, go over our methods and how we went about this process, review our results, and then summarize our final summary, and then see if there's any questions. So just to kind of get into this a little bit, some highlights that we identified were that there was excessive downtime due to machine failure, and then the second issue that we identified was there was a lack of machine information on just general machine health over time. And we really found that investigating those two areas were going to be worthwhile, and we'll get into it more. So we really developed a real-time error detection system for monitoring the cold rolling. And then also current monitoring through an IoT solution. So the impact here is that the solutions not only address Sukup's initial desires of monitoring their systems, but also move towards IoT 4.0 and more of a data-driven decision-making process. And so the next steps here are implementing a system that can shut down the machine when problems are detected, but we'll kind of review what is kind of going on here. So I'll pass it off to Jed.
All right, so for the objectives and assumptions, nothing here has really changed beyond what was first discussed in our first presentation. We're still looking to increase the average coil production by 1.7 coils per week by preventing major jams. We're also looking to identify minor issues before they become major, 50% sooner compared to the current monitoring state. And then we're also looking to implement an IoT dashboard that shows current and historical data on the current of the machine, or the amperage of the machine. Some assumptions and constraints. Again, these also have not changed, but we're still assuming here that the jams can take anywhere from 5 minutes to 3 hours to fix. The average weekly coil production is 27 coils. There's 40 hours of operation weekly on the machine. There will be utilization of extra product. Project costs are not discounted. Sukup chooses their sensors and brands and models for the final recommendations, so we'll provide final recommendations, but ultimately Sukup will choose. Supervision needs to happen when we work on equipment, so we have found that whenever we had to work on the machine, we needed to have supervision by either Haley or Tyler. Sensor spacing in and around the machine, so we had to work on, whenever we wired the different components, we had to work with the constraints of the machine in that regard. Limited machine capabilities, so there were limited things to monitor on the machine. It was essentially only current amperage. And then lastly, the machine designer was retired, so we had limited expert knowledge on the machine.
We'll kind of bring you through some alternatives here, just through both phase 1 and phase 2. For phase 1, as you can see here, some sensors that we were kind of looking to decide between to monitor the system were compliance sensors, angle sensors, and laser sensors. We really just wanted to make an educated decision that you'll see further on that is the most simple and most accurate. And then kind of going along with phase 1, we needed to choose the correct microcontroller. So a PLC system, an Arduino, an ESP32, or a Raspberry Pi are options here that we look to explore. Moving to phase 2, similar to phase 1, we needed a sensor that we needed to install both non-invasive or invasive trackers. And then on a database system side, we looked between Amazon Web Services and then the Arduino IoT Cloud platform. So we'll move here into methods, and Colton will take over.
So looking at the methods for phase 1, again, we had to decide between the microcontrollers. So on the table were Arduino, Raspberry Pi, and PLCs. Raspberry Pi presented the challenge of it ran off of an operating system instead of simple logic, and we only needed simple logic for this. So Raspberry Pi was going to end up being more complicated than it needed to be, and it would be harder to do the same task that an Arduino or PLC could do. Between a PLC and Arduino, PLCs have longer lasting components. However, they're definitely more expensive, about by an order of magnitude on average, for any individual part. And so we saw that prototyping with the Arduino system would work out the best in terms of figuring out which kinds of sensors to use, and then finally recommending a PLC system for the long-term solution after we finish the project. So once we've decided on Arduino, we started looking at different types of sensors that we could use, which included magnetic sensors, laser sensors, compliance switches, and linear distance sensors. And the biggest considerations here are, do the sensors need to make contact with the part rolling through the machine? And how complicated is it to take the data from the sensor in order to make a decision on it? And so, because of the way that the system is set up, we only really need a yes or no output from the sensor, which automatically made the linear distance sensor very overcomplicated for what we were doing, because that would give us an analog output of how far away it was, whereas all the other ones would give us a yes or no output. Then between the compliance switch and the magnetic sensors, we ran into issues of those would have to make contact with the steel rolling through the machine, which increased the chances of those sensors breaking and needing to be replaced or being miscalibrated. And because of that, we decided that the best solution to go with would be the laser sensors, because they make no contact with the machine. They're very easy to set up, and they're easy to fix if you make any mistakes with them on site. And so once we had that established, we worked with Sukup, both the engineers and the operators, in order to determine where to place these parts on the machine. And shown in the bottom right is the graphic of where we place all the sensors on the machine. So I'm going to pass it on to Jed to talk about phase 2 methodology.
All right, so for phase 2, we knew that we needed to measure the amperage of the machine. So again, there was limited things that we could monitor on the machine. We wanted to be able to gain a better understanding of the health of the machine. So really the only thing we could measure was amperage or current. So we had to find a sensor that could do that, and we wanted to find a non-invasive sensor. So we ended up finding a current transformer, which you can see in the blue there. It goes around a wire and can measure the amperage coming from that wire without having to actually invade into the wire itself. Next, we needed to use a microcontroller. So similar to phase 1, we needed to use a microcontroller, only this time we ended up choosing an ESP32. So this is very similar to an Arduino, only it has a Wi-Fi embedded chip. That way it can send and transfer data wirelessly, which is really what we were looking for an Industry 4.0 solution. That way the company Sukup could view real-time data on the cloud wherever they are located. And then we also had to create a breadboard with the circuitry, which you can see there in the bottom with all the different wires connecting the current transformer to the ESP32. And later we actually figured out that that was kind of a problem, but in the meantime, this was the solution we chose, that we didn't have to solder, and it was very minimalistic. And then lastly, we had to 3D print a case that would go around the breadboard that could be installed. So in the bottom right, you can see where the case with the breadboard, ESP32, and current transformer are installed. And you can see in the bottom left where the current transformer is around the wire in Sukup. So this solution was successfully installed into Sukup and was up and running. Next, we will talk about the results that we saw from each one of these phases. And I'll start with Colton on phase 1.
So in terms of phase 1, we had the final system to act as an extra set of eyes for the operators to catch issues early. And this ended up working out perfectly. We have all 3 different types of sensors installed, the L guide, the flat guide, and the when the coil runs out, and it will alert the operator, and it is currently up and running at Sukup. We completed a pre-install to figure out the best way to do things and how to fix issues that we ran into during that. And then through 2 more sessions, we were able to get the rest of the sensors installed. And so for moving forward with Sukup, we recommend that they replace what there currently is in the system with a PLC package. That way it'll be longer lasting, and we also recommend that a professional team installs this so that it has the capability of being wired into the machine's automatic shutdown, so that when issues are detected, it will stop the machine, thus detecting issues quicker and stopping the issues from growing in magnitude. So overall, phase 1 was a success, and Sukup was completely happy with how we installed it, and it has met their expectations with it. And now we are moving on to phase 2.
All right, so the results for phase 2. So the system was installed at Sukup on April 1st, and we gathered around a week's worth of data, but we noticed that the data was very inaccurate. And so what was going on was it was reading around 6 to 7 amps consistently. So what you can see in that bottom left-hand picture. This was inaccurate due to the amp clamp. So an amp clamp was used to measure the current, which reflected the correct current. And it was reading around 6 amps when it was idle, but then up to around 24 amps when the machine was actually running. And our system was not able to pick up this detection. And so we brought it back to Iowa State and then started doing some root cause analysis. And so we tested the system on a computer monitor. And the system was able to identify when the computer monitor was asleep and then when it was actually running. It was able to detect the jump in current. So we saw that it was able to work on a computer monitor, but wasn't able to work on Sukup's machine. And so we then wanted to test on a more industrial scale. So we went up to the Slater lab in Black Engineering and tested on an air compressor and additionally on a wood cutter. When testing these, we also noticed that, again, the amperage was maxing out around 6 amps. So on the air compressor, our system was reading 6 amps, where an amp clamp was reading around 12. And then on the saw, it was measuring around 6 amps when it was running, and then around 8 amps when it was actually cutting through a piece of metal, where our system was, again, just consistently reading 6 amps. So we knew that our system was maxing out, and we didn't know why. So then through a root cause analysis, we were able to figure out the problem was the breadboard. So the main infrastructure for the wire connections. And so the issue was a breadboard could only transfer around 5 to 6 amps through its system. And so this was why our system was maxing out around 6 amps. And so our recommendations to Sukup are to use a proto board or a PCB board. So a proto board would just require direct soldering to happen between the connections. So instead of pushing resistors or capacitors or leads into a breadboard, you would simply solder them together, which would then enable the correct amount of current to flow properly. Or a PCB board can be designed on a software and then can be ordered and shipped, which would prevent the need to solder. It just would take a lot more time and effort in design to create that PCB board. But ultimately, in order for Sukup to have a system that can detect the correct amount of amperage, a breadboard cannot be used, a proto board or a PCB board must be used to find the correct measurements. But our system itself and all the calculations, the coding, and the wiring was correct as it could read a computer monitor successfully, the detection between sleeping and running. So the only difference was a different core base, and that being a proto board or a PCB board. So next I will hand it off to Nick to cover the final summary.
Yeah, so here we have the income statement. It should be noted that this is the direct income statement that Sukup sent us. We see that in year 1 we'll easily have our return on investment with the implementation of phase 1 and phase 2. The big thing to note here is that over the 3-year period, we're looking at $3.5 million in savings. This is due to the production increase, and yeah, that's that here. And then looking at the phase 2 value proposition, one thing I just wanted to note is, in the analysis, some of the things that were factored in because it couldn't be directly, like production increase wasn't the direct factor here. Looking at like uptime analysis and accurate projections, downtime analysis and problem recognition, and then energy consumption were some important factors that went into perhaps the phase 2 ROI. One of the cool things about phase 2 in particular that I just wanted to mention is the time value of data. So you have real-time data, which is predictive and preventative. You have actionable data, reactive and historical. A lot of industries, and especially Sukup, as of right now, are using like more historical data. But hopefully, as they're pushing towards that Industry 4.0, we can look at predictive and preventative for them. Any questions? Yeah, and here's our appendix here.
Awesome. Thank you again. Awesome semester. Learned a lot, and we would like to conclude our final poster presentation. Thank you.